Now we will talk about free body diagrams of beam, what are the forces are coming on it. But before starting the free body diagram of beam, we have to understand the different kind of supports on the beam and what are the forces are coming on it. So first of all, we will talk about types of supports. So the types of supports, first one is fixed support. Then we will talk about hinge support, and then simple support. Simple support. So first, that is the fixed support. It is representing by this manner. So fixed support will not allow any kind of translatory motion or any kind of rotatory motion. So if we talk about fixed support reaction in 2D problem, so there will be a horizontal reaction, suppose Rx, and there will be a vertical reaction Ry, and there will be a movement. So whatever motion we are restricting, on the basis of that reaction will be generated at the support. In case of fixed support, we are restricting any motion is x direction, so there will be a reaction in x direction. We are restricting motion in the y direction, so there will be a reaction in y direction, and we are restricting any rotational movement, so there will be a moment reaction at the fixed support. So we can say that whatever motion we are restricting with the help of support, same kind of reaction will be developing at the support. Now talk about hinge support. Hinge support is representing by this way. Hinge support will not allow any translatory motion, but it allow the rotatory motion. So if we talk about the support reaction in 2D problem, so at hinge there will be a horizontal reaction and there will be a vertical reaction. For our coordinate axis we are saying Rx and Ry because we are restricting the motion in x and y direction. There will be a no moment reaction because we are allowing the rotatory motion above the hinge. Similarly, for simple support, we are representing by this way. In simple support, we are restricting motion only in one direction. Suppose I am representing the support by this way means we are restricting the vertical motion, so we are having Ry. Suppose sometimes we can represent the simple support. It depends on the application. So we will be restricting the motion in x direction. So there will be Rx reaction. So in case of simple support, we can say that reaction will be um, perpendicular to the in case of simple support we can say that there will be reaction Ry and Rx. It depends on the orientation of the support. Similarly, one more thing we can define for roller support, that is roller support. The roller support, normally we are representing roller support by this way. In roller support also the reaction, there will be only reaction. If suppose orientation is like that, there will be Ry, and if orientation is like that, there will be Rx, as same as simple support. But the difference between simple support and roller support, with the help of roller, we are minimizing the friction. So these are some of the examples of the supports and how the reaction will generate on it. So before going the free body diagram of any beam supported by this support, we should understand this thing. So now it is very clear to us what are the different supports and what are the different kinds of reaction will generate at each support on the basis of the loading. Now I would like to define the beam. So a beam is nothing but a structural member which is used for making the structure and is used for transferring the load or carrying the load. And the main geometrical feature of the beam is cross-sectional dimensions are negligible in comparison. So again we can define the beam. Beam is nothing but a structural member which is used in forming the structure. With the help of beam we can transferring the load beam, or we can say that with the help of beam it can carry the load. The geometrical feature of the beam is the cross-sectional dimensions of the beam are negligible in comparison to the length. Means length of the beam is more in comparison to other dimensions. So now we are interested in classification of beam. Classification of beam. So first one is cantilever beam. Cantilever beam. In case of cantilever beam, one end is fixed and other end is free. That is cantilever beam. Second one, that is simply supported beam. Simply supported beam. In simply supported beam, both ends of the beam are supported with the help of simple support. Third one is continuous beam. In case of continuous beam, the number of supports are more than 2. This is called continuous beam. Fourth one is overhanging beam. In case of overhanging beam, the some portion of the beam is beyond the support. So this portion of the beam, let's say AB, is beyond the support. So that's why this beam is called overhanging beam. So it was all about the beam, the definition of beam and the classification of beam. Let's take a problem which is based on equilibrium so that our understanding on equilibrium will be more. So ABCD is a string. I am drawing the string. It is A, B, C and D is a string suspended from point A and point D and carries a weight of 5 Newton at B and a weight W Newton at C. The inclination to the vertical of AB is 45 degree and the inclination of CD with vertical is 30 degree. And the angle ABC is 165. Angle ABC is 165 degree. Now we have to find W. So for this problem our objective is we have to find W. So now if we see the diagram here, the string is ABCD and this string is in equilibrium because the forces are acting on a string and the string is in rest, so we can say that the system is in equilibrium. And if the system is in equilibrium, so we can easily apply the conditions of equilibrium. So for solving any problems based on equilibrium, first of all we have to draw the free body diagram. So first step to draw free body diagram. So let's draw the free body diagram of point B. At point B, there is a force 5 Newton which is acting in vertically downward direction. There is two string AB and BC is coming on point A. So there will be a tension in AB, suppose it is T1, and BC it will be suppose T2. And now the angle here, we know that this one is the 165 angle. This angle is nothing but because here we are having 45 and this full angle which is 180 degree. So 180 degree minus 45, it will be 135 degree. And here we are having this angle 45, this angle 165. So this angle will be 120. So the remaining angle for the linear line, it will be total angle is 180. So this one will be 180 minus 120. It will be 60 degree. So now we have a special case of equilibrium. A special case of equilibrium for 2D problem, especially for three coplanar concurrent force system, that is Lami's theorem. So if we apply Lami's theorem for this point, for this FBD, so according to the Lami's theorem, we can write T1 and sine of the angle between opposite two forces will be sine 60. Similarly, T2 sine of the angle between the opposite two forces, it will be 1 sine 135 degree, and 5 Newton sine of the angle between the opposite two forces, it will be sine 165 degree. So with the help of these two equations, we can find out T1, and with the help of these two equations, we can find out T2. So one by one, we will take these two equations. So T1 equals to 5 by sine 165 degree into sine 60 degree. So 5 sine 60 is nothing but 0.86602 divided by sine 165 0.2582. So the T1 will come around 16.73. Similarly, by taking other equation, T2 equals to 5 into sine 135 degree divided by sine 165 degree. So 5 sine 135 degree is 0.707 divided by 0.2588. This one will come 13.66 meter. So by this way we can find out the value of T1 and T2. Now talk about free body diagram of point C. So point C, there will be a downward force W, then here BC is there, CD. So BC we know tension is T2, and here we can define the tension T3. And if we talk about angles, this one is 30 degree. So obviously this one will be 180 minus 30, it is 150 degree. And if we talk about these two angles, that is between T2 and W and T2 by 30 we can easily find out from here. We are having this thing 165 degree here. This is so these angles are alternate angles here. Here we are having these two parallel lines. So this angle we know this angle is 120 degree. So obviously this angle will be 120 here by alternate angles. So we can define here this angle will be 120, and if it is 120, so the remaining angle will be 60 degree. So now we can easily apply the Lami's theorem here. So Lami's theorem, according to Lami's theorem, W sine of the angle between opposite two forces, it is 60 plus 30, that is sine 90, plus to T2 divided by sine 150 equals to T3 divided by sine of the angle between opposite two forces 120, and we already know the value of T2, so we have to pick this equation. So by this equation W equals to T2 into sine 90 divided by sine 150. Sine 90 is 1, T2 we know 13.66 into 1, sine 50 is 0.5. So by this way we can get the value of W, nothing but 27.32 Newton. So by this way we can easily find out the value of W with the help of Lami's theorem. But for solving this problem, make sure whatever angles we are taking, it should be correct angle. So just think about the angles, what are the different angles and what are the values, and just by applying the Lami's theorem, you can easily find out the value of W. Let's take another problem of equilibrium. It's a very interesting problem. There is a beam AB which is hinged at a point B, which is hinged at a point B, which is hinged at a point A, and the other end B is connected with a string through two pulleys as shown in figure bracket. It's connected with the two pulleys here. And this pulley is carrying a load W, and the length of the AB is L, and these two pulleys are frictionless pulleys. Now we are interested in the point of application of force P such that the whole system is in equilibrium. I will just again repeat the problem. There is a beam AB. A point is supported by hinge joint. B is attached with the string which is connected with these two pulleys, and here we are applying the load W, and here we are applying the load P. Now we have to find out the point of application of the P from A such that the whole system is in equilibrium. So basically it's a problem of equilibrium, and for attempting this problem, first of all we have to draw the free body diagram. So I am drawing the free body diagram of pulley carrying weight W. Free body diagram of pulley carrying load W. So the free body diagram of this pulley, there is a weight W acting in a vertically downward direction, and the string is going like that. So there will be a tension here. It's a continuous string. It's a continuous string, so the tension will be uniform. So we can say that tension here is T, so here it will be T. So now after drawing the free body diagram, we can apply the conditions of equilibrium. So by saying this, we can say that if it is in equilibrium, then net force and net moment will be zero. So there is only the vertical forces are acting on it. So directly we can apply the condition number 2. Algebraic summation of all vertical forces should be zero if the body is in equilibrium. So this both the tension Tt are acting in a vertically upward direction. First assume the sign convention. Vertically upward is positive, vertically downward is negative. So T, these are acting in a vertically upward direction, so it will be positive, so plus T, and weight it is acting in vertical downward direction, so according to sign convention it is negative, so minus W equals to 0. So if we solving this equation, 2T equals to W, so T equals to W by 2. By this way we can find the value of T in terms of W. Now draw the free body diagram of AB. Free body diagram of AB. So first of all we have to isolate AB from other bodies from the definition of free body diagram. A is hinge joint, so there will be a horizontal reaction. Suppose Rx, and there will be a vertical reaction RAY. P already acting on a body, suppose the distance is x, and here the tension and the string is uniform, so again it will be T, and we know T is nothing but W. So we are interested in the value of x. We have to find x. So now we are having free body diagram, so we can apply the conditions of equilibrium. But our interest is only in x. We are not interested in the value of Rx and Ra. But we have three equations. We can find out three unknowns. But we are interested only in x. So if we apply the moment equation about A, so by this one equation we can easily find out the value of x. So what is the moment equation for equilibrium? Algebraic summation of moments of all the force about A should be 0. And if we see the line of action of Rax and Ray is passing through A, so perpendicular distance will be 0. So moment at A due to Rax due to Ray will be 0 because perpendicular distance is 0. Moment at A due to P. So P and this distance, this is nothing but x. So P into x. And if we see the direction of rotation, it is clockwise. So according to our convention, clockwise is positive, anti-clockwise is negative. So this should be plus. And the moment due to this T, so T here and the distance here, this is L. So this distance will be L minus x. So moment due to this T at A will be T into, okay, we are not interested in L minus x. Perpendicular distance is directly given, that is L. So this one is L. And the direction of rotation is anti-clockwise, so it is negative. This is 0. So by this equation we can write Px equals to TL. So x equals to T into L by P, and we know the value of T in terms of W is W by 2 L P. So our final equation will be WL by 2P. So the X will be WL by 2P. So by simply only one equation we can find out the value of X. So after drawing the free body diagram and in which quantity we are interested. Here we are interested only in x. So we have to think by with one equation how we can solve it. whether we have to go for horizontal equation like algebraic summation of all the horizontal forces should be zero, or algebraic summation of all the vertical forces should be zero, or algebraic summation of moments of all the force above v1 should be zero. So according to our interest, we can pick any of the equation and we can easily solve the question and we can save our time.